First aspect of properties of matter that we look into is the property of elasticity. So when a material is placed under stress, it tends to get deformed. But all materials have a tendency to retain their original shape or restore themselves to their original shape when the deforming stress is removed. And that is the property of elasticity. Like the most obvious example is the elasticity or elastic property of a spring or a rubber band. Okay, but all materials have to a certain extent the similar kind of property, which is called elasticity. So elasticity is the property whereby any material deformed from its natural shape due to the action of external forces has a tendency to so this tendency to retain or restore itself to its original shape is called the elasticity of a material. So the origin of elasticity is the nature of so if we study the relationship between interactions between molecules in all materials, then the bond energy versus distance is usually some kind of you can see from this that if the distance r is increased or decreased by external factors, the intermolecular force, which is minus du by dr, is restorative in nature. So this creates the property of elasticity. Just make a note of this part. We'll continue from here. Yeah, Aruja. So the graph basically explains the intermolecular bond energy, or potential energy related to the intermolecular attractive force. Okay. So you can see that it has a minima, local minima, at a bond length of r equal to r naught. So when the distance between molecules is a certain optimal bond length r naught, the energy associated with their intermolecular force is at the local minima. That means there is a stable equilibrium position. Okay. And as you know, the relationship between internal force and potential energy is negative gradient. Okay. So we have this relation that F is equal to minus du by dr. So this is the conservative force. So this force is equal to 0 at r equal to r naught. But for r greater than r naught, you can see that the force becomes negative. And for r less than r naught, the force becomes positive. So it's restorative in nature. It tends to restore it back to r equal to r naught. So hope it is clear now. Okay. Next up, we look at the concept of stress and strain. So in general, stress is defined as force per unit area that causes deformation in a body. So we will see different types of examples. So there are three types of stresses. Longitudinal or tensile stress. So if we have a body whose length is L, but we subject it to external forces which are causing it to elongate like this. So this force will also create an internal tension. And if it has a cross-sectional area, of E, then the longitudinal stress is defined as tension per unit cross-sectional area. So this can happen both ways. We can apply external force in such a way that it either elongates or it compresses. In both cases, it will create tensile stress because tension will develop along the length of the rod as an internal force like this, or the length of the material. And in this case now it is in a compressed state. Okay, now simultaneously we'll also understand the concept of strain. So longitudinal strain, it is defined as where delta L is the magnitude of change in length. So it is the fractional change in length. So stress is always defined in such a way that it has dimension of force per unit area, and stress is measured in newtons per meter square, and strain is always measured in such a way that it is dimensionless or unitless. Okay, now let's move on to the next type of stress and strain. Yeah, Varun, to answer your question, rod may or may not be massless. Okay, so both situations, the definition of stress is regardless of that. Okay, and Aruja, to answer your question, tension is always perpendicular to the length of the rod, whether it is compressed or extended. In all cases, in both the diagrams, you can see tension acts along the length of the rod, perpendicular to its cross section. Okay. So this is in both cases. The situation is both for compression and for extension. I hope this is clear. Okay. Next type of stress and strain we'll see is called shearing. So when a body which is of natural shape like this is subjected to external force which acts tangential to its surface to sort of bend it like this, then we say that it is under the action of shearing stress, which creates shearing strain. So if external force is applied tangentially to a surface like this, so this has area A, causing the body to bend like this to an angle theta. So this is under a sheared state or deformed. So shearing stress is defined as tangential force per unit area. So tangentially means along the surface. And shearing strain is the angle by which it bends, which then approximately becomes x by L because it's a small angle. Okay, so this is the second type of stress and strain. Okay, and the third and final type of deformity and related stress and strain we'll talk about is the volume stress and strain. So when a three-dimensional object of natural volume, let's say V, when it is subjected to standard action, so this is when it is subjected to higher pressure, it tend to compress in volume. So it is under volumetric compression. So the volumetric stress is defined as the excess pressure, whereas the volumetric strain is defined as the change in volume upon original volume. Such a body can also experience its volume could expand to V plus delta V because of a decrease in external pressure. So one important point here is that here delta P and delta V are defined with sign, with algebraic sign. So therefore, expansion means that delta P will be a negative quantity and delta V will be positive. Whereas in compression, delta P will be written with a positive sign. So there is positive volumetric stress, whereas delta V will be negative. So there will be negative volume strain. So these are the three types of stress and strain. And understanding the relationship between stress and strain is what this chapter of elasticity is all about. Okay, so next, what we'll understand is the relationship between stress and strain. So, the study of elastic behavior and also related to this is something called Hooke's law. So the statement of Hooke's law is basically like this, that for any material under stress, whichever type of stress, okay, but up to a certain limit, called the proportionality limit. Stress and strain are directly proportionate. And the constant of proportionality, or the ratio of stress and strain, is called the modulus of elasticity, which is a physical property for a given material. Okay, hence, this comes under a category of properties of materials. Another important aspect is elastic limit. Of stress. So there is a maximum limit of stress, which is called the elastic limit, up till which the body displays elasticity. That is, it can restore itself to its natural state or shape when the stress is released. Okay. So for stress greater than this elastic limit, okay, a material or body exhibits plasticity or plastic behavior. That is, it becomes permanently deformed. Like if you stretch a rubber band too much, okay, it might of course break, but before it reaches that breaking point, it can also get elongated in such a way that it loses its property of trying to retain its original shape, or it loses its property of elasticity. So when that happens, we say that the material is behaving in a plastic manner, or it's showing plasticity as opposed to elasticity.
Sir,
Yeah, sorry.
sir, can you please explain the proportionality limit?
Yeah, I'll be explaining with examples. Okay. Okay, I'll just scroll up once. People are writing down. So what happens is, let's say we have a material or a body at a natural shape to begin with, and we start applying stress which we are gradually increasing. So as we are increasing the stress, the amount of deformity or strain also increases. So initially, stress and strain, they behave in such a way that they are proportionate. So the amount of strain is proportionate to the amount of stress. But beyond a certain limit, that proportionality goes away. It becomes a non-linear behavior. So that limit is called the proportionality limit. And up to a certain limit of stress, what happens is that if we release the stress, the material will come back to its original shape. So that is called the elastic property of the material. So it behaves elastically. But if the stress is increased beyond a certain limit called the elastic limit, then it does not display elasticity anymore. It has some permanent deformation. And that is called the plastic behavior. So for stress greater than elastic limit, the material loses its elasticity and becomes plastic in nature. And finally, at a certain value of stress called the breaking stress, not only the material is permanently deformed, but it will fracture or break at its weakest point when subjected to that kind of high stress. Okay, so now imagine, suppose we are doing an experiment where we are gradually increasing the stress and measuring the amount of strain for a given type of situation. Let's say we are measuring longitudinal stress and longitudinal strain by doing something like this, that we have a thin metallic wire like this, which is of known length, known natural length, and so it's very light. It has a natural length L and area of cross section E. Now what we do is we attach something here whereby we can gradually increase the mass. So what is happening in this case is that as we increase the mass, the tension will also accordingly increase. So the longitudinal stress, and as a result of that, the longitudinal strain will be like this. So if we are doing an experiment where we are gradually increasing this mass, so we are able to control the amount of stress by controlling the amount of mass. So we are gradually increasing the stress and we measure the strain. That is, we measure the length. So from that we know how much delta L is. So we are able to observe the relationship between the applied stress and the amount of strain caused by it. So then what we will see is that the nature of this graph is such that initially, starting from the point 0, there will be a linear behavior. Okay. But that linear behavior will last up to a certain limit. And that limit is called the elastic limit. Oh, sorry, the proportionality limit. Now, beyond the proportionality limit, the strain starts to increase disproportionately. So it starts to become curved like this. The expected behavior would have been like this. But for small changes in stress, there are larger equivalent changes in strain. So that is when, okay. And also what will happen is this part of the graph, it is both ways. So if we start reducing the stress, the graph will come back to its original shape. But once we cross a certain limit called the elastic limit, two things. We observe that the amount of strain starts increasing more disproportionately. And also, if we take it to a certain point here and then start reducing the stress, you'll see it does not come back to its original shape. It shows some permanent deformity. Sorry, the graph is reverse. The applied stress is on the y-axis. The strain is the x-axis. Okay. So what we observe is that if we start reducing the stress, okay, beyond the elastic limit, once we have gone beyond the elastic limit, the reverse diagram is like this. There is permanent deformation or permanent strain. So that is the behavior of plasticity. But to exhibit plasticity, we have to take it beyond the elastic limit. And then at a certain value of stress, we reach the breaking point. So as we have seen before, for stress less than equal to the proportionality limit, stress and strain are proportionate to each other. For stress greater than proportionality limit, there's a non-linear behavior between stress and strain. And for stress greater than the elastic limit, there is permanent deformation and plasticity. Whereas for this type of stress, the material behaves elastically. That is, if we release the external stress, it will tend to come back to the natural shape. So this is the experimentally observed behavior for wide variety of materials to different types of stress and strain. This graph is valid, though I have shown the diagram, the experimental apparatus beside only for a situation where we are measuring longitudinal stress and strain. But if we do a similar experiment for shearing stress and strain or volumetric stress and strain, we get a similar kind of relationship. The values will be different. The value of proportionality limit, the value of elastic limit will be different for the different types of elasticity and different for different materials. But the general nature of the graph will be similar. It always start with a linear kind of relationship, direct proportionality. Then it will go on to non-linear behavior. And somewhere along the line in non-linear behavior, the material yields to the stress. Yields means it shows permanent deformation. So when we release the stress, it does not have a tendency to come back to its natural shape. It's got a permanent deformation. And of course, every material, no matter how strong or how weak, has a breaking stress. Okay, so this is the basic theory part in this chapter. Now, when it comes to the application and the numericals, it's limited to the application of Hooke's law only, because that is the only part which is predictable, right? Where the behavior is such that it's linear, so we can represent it by an equation. So Hooke's law and applications, let's understand that. So the basic statement of Hooke's law we've already seen, that stress is proportional to strain, of course subject to the condition that the stress is within the limit called the proportionality limit. Okay, and the ratio of stress and strain is a constant called the modulus of elasticity. So again, this comes in three situations. For longitudinal deformity, we have the ratio of longitudinal stress to longitudinal strain, which can be written as tension per unit area divided by fractional change in length. This is given by a modulus called Young's modulus of elasticity. Which is a material property. Similarly, we have for a shearing situation. And similarly, we have for volumetric stress and strain also. So we'll come to these. So for example, metals have Young's modulus typically of the order of magnitude of 10 raised power 11 Newton per meter square. Okay. So coming back to longitudinal stress and strain and Young's modulus. So let's look at application of this formula. So here in this relationship is of course Hooke's law. Two things to understand, that of course the stress should be less than equal to the proportionality limit. The other thing is that delta L over here is the magnitude of change in length. So it's does not have sign. That is how it is defined. So let's look at an example application of this. So just to understand the type of values involved, okay, let's look at a typical practical example. So let's say we have metallic wire. Okay. So it's of negligible mass. Now its natural length is, let's say, 5 meters. Its area of cross section is, let us say, 4 millimeters square, and the Young's modulus is, let's say, 2 into 10 raised power 11 for that particular metal. Okay. Remember, modulus of elasticity will have the same dimension as stress. Force per unit area, because strain is dimensionless. And now what we are doing is we are hanging a mass over here of, let's say, 50 kilograms. We'll take G as 10 meters per second square. So that creates a tension which creates a stress, uniform tension because it's massless. Okay. And as a result of that, this gets elongated. So this gets elongated to L plus delta L. So now we want to find the longitudinal stress in the wire, the strain, and from that the elongation. These three things we want to find out. Okay. So whenever we are given a numerical problem like this, we will have to assume that the stress is within the proportionality limit, because otherwise there's no point. We cannot apply Hooke's law. So all numerical analysis will be with the assumption that we are able to apply Hooke's law. That is, the stress is within the proportionality limit. Not only is within the elastic limit, but it's actually within the proportionality limit. So the rest of it is the normal application of mechanics kind of principle. So if you make the free body diagram of the block, you can see the weight is balanced by the tension, because the block is at rest. So the tension in the wire will be equal to the weight of the block, which is equal to 500 newtons in this case. Okay. So the first part, the longitudinal stress, will be tension per unit cross-sectional area. So 500 newtons divided by 4 millimeters square. So we will write that as 4 into 10 raised power minus 6. So as you can see, the stress will become 1.25 into 10 raised power 8 Newton per meter square. So this is the answer to longitudinal stress. So now applying Hooke's law for the second part, we'll just apply this, that longitudinal stress upon longitudinal strain equals to Young's modulus. So reversing this equation, the strain becomes stress divided by Young's modulus. This is our longitudinal strain. Okay, so I'll just minimize this a little. You can calculation once more, but it's very straightforward actually. Okay, so now once we have calculated this, from this we can calculate the value of delta L. That will be the strain multiplied by the original length. So 6.25 into 10 raised power minus 4. Remember, is a dimensionless factor into 5 meters, which was the natural length. Okay. So this will become 3.125 into 10 raised power minus 3 meters. Okay. Or 3.125 millimeters. That will be the amount of extension created. Okay, let's look at another example next. So suppose we have this kind of situation. We have a heavy slab like this. Now this is supported by pillars like this. So a heavy concrete slab. Its mass is, let's say, 10,000 kilograms. Okay. It's supported by 4 identical concrete pillars, which are light in weight. In comparison to the slab, they are much lighter in weight. Okay. In fact, let's make them metallic pillars. Okay. They have Young's modulus equal to this much. Cross-sectional area 20 centimeters square each. Okay. And natural length of 1 meter. So you want to again calculate the stress, strain, and the compression for each pillar. So it's not exactly that metallic pillars of this kind of size will be massless, but their mass is negligible compared to the heavy concrete slab, which is 10,000 kgs. Okay, so we will take them as extremely light. This slide is how people will discuss. Yes, Shreya, you have a doubt, beta?
So should I resend you on WhatsApp?
Sorry? What was that again, beta?
Sir, this is Kripa. Can I send you all of my doubts on WhatsApp?
Yeah, you can send the doubts on WhatsApp. Yeah. Okay, so let's check out the value of stress on each of the rods. So you can understand that the rods will be applying tension like this. Okay. So by symmetry, each will have equal amount of tension. So the weight of the concrete slab is balanced by the total tension of 4T. Okay, so tension on each rod is 1/4 of the weight. So 2.5 into 10 raised power 4 newtons is the tension in each. So accordingly, the stress in each rod, the longitudinal stress, okay, so many of you have not done this, not divided the mg by 4 for the tension in each rod. So please take note that it will be like this. Okay. Also, you have to convert to SI units. So this is meter square. Okay. So longitudinal strain, and from that we can find the compression. So there's this much compression in each of the rods. Okay. So with this, people, we conclude today's session, and we will come to more applications and examples, including sharing stress and strain, in the next lecture. Okay. So that's it for today's session, people. Thanks for attending and wish you all the best. Yeah, you can start doing questions from HC Verma Aruja directly. Okay. From the chapter on elasticity, you can try out the first 15 questions or first 12 questions, actually 1 to 12. You can do those questions. Okay.
Sir,
Yeah,
sir, I have from major test 9. So can we do that in the next lecture?
you have doubts from major test 9.
Yeah.
I think we will schedule a doubt session for the major test discussion. No? Then we'll schedule a session separately for that.
Okay, sir. Bye, sir. Thank you, sir.
Okay, okay, well, that's it for today.